Okay, so continue from the last lecture. Let us continue with the brief review of thermodynamics that we started up with, right. So, the first property that we will talk about is internal energy. Okay. So, this is typically how we denote internal energy. So, the internal energy of a particle can happen because of several motions. Right. Now, we are not interested, like we said in the previous lecture, we are not interested in the individual movements or contribution to energy. Right. We are not interested how an individual particle has its energy from. What we are interested is is a conglomeration of particles, which we call as continuum. So, therefore, this is also a macroscopic property, and a sum total of all these individual energies in whatever way they are generated is the internal energy of a fluid, right. Now, so we will call this as a specific internal energy, and this is basically the internal energy per unit mass. Okay. And at the same time, this H is another quantity which is called the enthalpy, and again this is specific enthalpy, is enthalpy per unit mass, and this is my relationship. Now, for a real gas, right, for a real gas, well, take a guess. What does the internal energy and enthalpy depend on for a real gas? Like, compare that with what we said about a perfect gas, right. So, the internal energy depends on temperature, the enthalpy also depends on temperature. I think it is easy to see here. So, the internal energy depends on the volume and temperature, and the enthalpy depends on the temperature and pressure of the fluid. So, these relationships are essentially for a real gas, right. Now, like we did in the previous case, let us define two more concepts here. One is the the thermally perfect gas. Okay. The thermally perfect gas. So, that would mean what does that mean? In the how is that different from what we defined over here, a thermally perfect gas? Right. So, these properties now depend only on the temperature, right. So, hence this is the definition of thermally perfect gas. Now, in this case, I think that is easy to see. It's when I write equations like this, I kind of spell it out. Say that in words, it kind of makes more meaning to me. Now, CV is the what is specific heat at constant volume. So, what is CV? It is a specific heat at constant volume. So, in this case, this is nothing but the change in internal energy per unit change in temperature, and this is a specific heat at constant pressure, and this is dH by dt, that is the fractional change in enthalpy per unit change in temperature, right. So, now both these parameters here, CV and Cp, are, as you can see, they are both functions of temperature, right. Okay. So, this is a thermally perfect gas, and this is a what do we mean by a calorically perfect gas. A calorically perfect gas is so. Right. So, in this case the assumption is that at T is equal to 0, right. So, we see examples of this also in practical applications of compressible flow. So, therefore, these relationships, we kind of do this a lot in fluid mechanics. We label, give labels like this: thermally perfect gas, calorically perfect gas, incompressible flow, viscous flows, compressible flows, incompressible compressible flow, and so on and so forth. So, inviscid compressible flow, sorry. So, we do that because then we are able to develop relationships like this, which can be used for a large bracket of problems, right. And it kind of helps us not to go and solve very generic equations. So, this gives us more usable equations, more usable relationships for a particular bracket of problems that fall under that category. So, this is also when we consider a calorically perfect gas. So, we would have a large number of problems under this category, and we should be able to use these relationships with a lot of ease. Okay, I think let us now move on to let us look at this relationship. Okay. Now, this is probably you are familiar with this. Okay. This is nothing but the first law of thermodynamics. Okay. Now, let us look at each term separately, right. Now, so therefore, now here, so this dq is a quantity of heat, this is a quantity of work done, and this is a quantity of energy. And we have these delta, delta and d. So, dE is a change in energy, dQ and dW is the corresponding changes in heat and work. Okay. Now, this is defined over a system. Okay. So, this is defined over a system. Now, I talked about what a continuum is in the last lecture. Now, what exactly is a system? How is that different from a continuum? Okay. So, what makes a system? So, you can read up the general definitions in a book, but think of an example of what you can call as a system. We have systems around us all the time. Now, for example, say you have fever, right. You have fever and you use a thermometer to take your temperature. Now, you place, so basically in this case you are the system, right. You are the system and you take the thermometer and take your temperature, right. So, then you are looking at the temperature profile, say, of you, which is the system in this case. Now, in this case suddenly there you have a heater, say nearby yourself. So, in that case, if you are taking your temperature in that case, when you have a heater nearby, right. So, then the temperature will show slightly different than what your individual temperature is. So, we do not want that, we want only your temperature. So, in that case what we will do is, say we will take you and we will put a surface around you, we will put a Mach boundary around you, right. So, this will be a surface and this will be a boundary which will mark my system, which in this case was you. So, then this becomes my system and this is my boundary. So, this boundary is not any tangible box, it is not like it is a wooden box or a steel bar, nothing like that. It is just a imaginary boundary. Is basically we are saying that if you are going to take the temperature. If we are interested in a certain temperature, we are interested just in this. So, this is something which will cordon off, so to speak. So, this system. So, this piece of material, in this case this piece of mechanism, in this case the mechanism being a human being. So, and then this becomes your system, and you are going to study your properties, in this case temperature change, only on this system. So, that is basically your system. Okay. So, now the next thing to ask here is that what do you make of these symbols? On the right hand side we see a dE, right, and here we see deltas. Is that I just write it like that, or I have a specific reason why I write it like this? Can I just write whatever I want? Can I just write d? Why didn't I write dW and dQ over here, or for that matter why didn't I write delta over here? I wrote delta W and delta Q, and I wrote dE. What is the reason for that? Okay, so now let us try and see if we understand that. So, dE is a change in the internal energy, right. Now, the dE is essentially a change. So, say we have a certain change in, so say this is a point A, and say this is a point B, right. So, these are basically say two different levels of energy. Okay. Okay. Now, say I move from A to B in this fashion. I follow this route, right, I follow that route, or say I move from this pattern that one in this way, right, or I say I move in this fashion. What happens to my dE? So, do I have 3 different dEs? The answer to that is no. Okay. So, in this case dE is only basically, which means the final energy minus the initial energy. So, it does not depend on the path. So, this change is independent of the path, it is path independent. Okay. It does not matter how you go from A to B. All that we are concerned about is the final value minus the initial value. So, therefore, we write that as dE. Okay. Now, I think by this time you can infer that delta W and delta Q on the other hand are path dependent, okay, are path dependent, and there are more than one ways of adding heat and doing work, and therefore, we write these as deltas. Okay. So, when I say that, so therefore, when there is more than one ways of doing work and heat, what could we can categorize these ways as well. Okay. So, there are basically 3 categories of that. We will, I think, understand a little more as we go along, but briefly for now we will write that what are those processes essentially. So, essentially this is when I say it is an adiabatic process, a reversible process, and an isentropic process. Okay. Now, an adiabatic process is one where the net heat supplied to the system is 0. Okay. Reversible process is something, the process is reversible. Okay. You take a process from say A to B, then you are able to bring back the system exactly to its original state. Goes from one state to the other, comes back exactly to the same state, that is reversible. So, when that happens, obviously we do not have any sort of dissipative mechanisms like this conductivity, this viscosity, and so on and so forth. Okay. Chemical reactions are of course not considered when we are considering things over here. And isentropic process is one which is both adiabatic as well as reversible. Okay. Now, the moment we talk about, so now this becomes an important concept here. We will come to that in a little bit. Now, let us go back one more time over here. This is the first law of thermodynamics, which says that for a given system, the energy change is a function or is equal to basically the heat supplied plus the work done, right. Now, let me give you two scenarios. Okay. Let me give you two scenarios. Now, I have say I have an ice cream. Okay. I have say a bowl of ice cream, a tub of ice cream, call it whatever you want. Okay. I have an ice cream. Okay. And let me just, okay. So, this is my ice cream, and what I do is I take that and I put it on this plate, and this plate say is slightly hot. It's kind of a, it's a heated plate. Okay, slightly hot plate. It's not exactly at room temperature. Okay. Now, you are probably guessing what will happen, but let me give you two scenarios. Okay. Now, one scenario is that the ice cream melts, right, and this temperature drops slightly, right. So, we have the ice cream melts and colder, let us say colder, or if the temperature drops slightly. Okay. That is one scenario. Now, the other scenario is, that the ice cream actually does not melt, the opposite happens, the ice cream actually freezes even more, and the plate becomes hotter. Right. So, in this case, this is something you probably you would expect it, right. So, the ice cream melts and the plate becomes slightly, the temperature of the plate drops. On the other hand, so there is a certain energy change here, you can see that, right, there is certain energy change here. In this case, the ice cream freezes even more than what it was, and the plate actually becomes hotter, right. And this has the same energy change. The energy change here is exactly the same as it is here of the system. If there is just give and take between, there is a certain give and take between the two within this system, the ice cream and the plate, right. So, the total energy change is still dE, whether you do this or do that. So, what is the problem over here? Well, clearly in nature this does not happen, clearly in nature that does not happen. So, what happens is this, the first scenario. Now, can we say for sure that this is what will happen from the first law of thermodynamics? At least I can't tell. This equation does not tell me that in what way heat should be generated, in which way heat should be generated, and how work should be done by the system, right. So, all this tells me is that the net energy depends on more than one ways of providing heat or work. So, as far as this equation goes, both these scenarios should work, but clearly it does not. So, therefore, obviously that will not happen. So, this happens. So, in that case we need something else. We need another relationship which really gives us a direction in which the heat and heat will flow and work will happen, right. So, what is that relationship? Now, that relationship is essentially the second law of thermodynamics. So, therefore, this is not sufficient. This is not a sufficient condition. So, that is where we come up with the second law of thermodynamics, and let me write that here, right. Okay. So, what the second law says in this case, we introduce something like this. The entropy, the concept of entropy, that for a system, the process will happen in such a way that the entropy of the system is always increasing, okay, and at least it is constant. So, that this is the second law of thermodynamics, and this gives us a condition in which should be adhered to when the system is proceeding. So, unlike in this first equation, which does not really give us any clue as to in which direction the process should be proceeding. So, that is given by the second law of thermodynamics, that is the concept of entropy. Okay. So, so let me sort of do a little bit, explain that a little bit more. Okay. Now, for example, if we had to look like this, now for example, there is a pressure, this is a PV plot. Okay. So, this is a volume and pressure. Okay. Right. Now, if I take this integral, what do we get? So, essentially what I am saying is that for a given for a certain pressure, I have a change in volume, right. So, there is a pressure that is creating a change in volume, which is dV. This is nothing but the work done, right. This is the work done. So, mathematically all we are doing here is taking the area under this part of the curve. So, that is the integral. So, this is the integral. So, pressure into the change in volume gives us the work done. Now, similarly, so if I may just do it over here. Right. So, if I take this integral over here, what is this? So, this is temperature and this is the entropy. Okay. This is the temperature, this is the entropy. If I take this integral, well, the entropy change into the temperature gives us what? This is what gives us the heat. This is gives us the heat supply. So, in this case, we have this area under the curve, this area under this Ts curve. So, this is basically the entropy. So, which means if I had to write it from there, if I just use that expression, right, if I use that expression, right. So, that should give you some idea. So, if you had to, measure say entropy, what would you do? So, therefore, what we do is the change in the heat, right, the change in heat supply or the heat supply by the temperature, that is the entropy change, right. So, this is the concept of entropy, and so therefore, heat is going to be supplied. So, as you can see here that heat is going to be supplied in such a way that the entropy is always positive, right. Its entropy is always positive. So, why do not I write it like this, right. So, at least it is equal to this, the heat is supplied in such a way that ds is equal to dq by T and it is increasing. So, this is your concept of entropy, which is given by the second law of thermodynamics. Okay. Now, what we will do is we will sort of look at some of the relationships, right, which we drew up, and we will just see how they look like, because we have defined so many things. We said real gas, then we said thermally perfect gas, calorically perfect gas, so isentropic process. So, we have kind of sort of been around the block, so to speak. So, what we will do is just look at a few relationships which you have probably you are familiar with. So, we will kind of make sure that we understand what those whatever we have learned so far. So, we understand that. Okay. So, okay, so I think you will remember this expression. Right. Now, these relationships are for a real gas. So, you must be familiar with this, right. So, the the gamma is the ratio of the specific heats. So, these are relationships for a real gas, and now for a calorically perfect gas, you remember what that was? We just said that. What was calorically perfect gas? So, calorically perfect gas is this. This is the relationship between the specific heats, temperature, internal energy and enthalpy. Okay. So, this is the calorically perfect gas. So, in this case, so I will get typical relationship like this. Okay, or you can write this as well. So, this is So, this is basically for a calorically perfect gas. So, these are relationships for a calorically perfect gas, and then so isentropic process. An isentropic process is adiabatic, reversible, and what is the mathematical quantification of that? That the entropy is constant, right. So, ds is 0, right. So, as we just said, ds is 0. So, in that case we get relationships like this. Okay. Now, so this is just to kind of familiarize you with the kind of equations or relationships that we will be working with when we say a real gas, when we say a chlorically perfect gas, isentropic process. So, like I said at the start of this lecture, that we constantly kind of do that, because then it gives us a lot of workable relationships in this fashion, and there are practical problems in which large number of practical problems or bracketed problems for which we can use this sort of these relationships. So, these are very handbook kind of relationships that we can use. Now, one more thing to ask here is, what do we mean by this? What are these subscripts mean? What do these subscripts mean? 2, 1 here. I seem to be writing that everywhere. What do these mean? S2 minus S1, T2 by T1, P2 by P1. What does that mean? Right. So, what that essentially means here is pretty much like we talked about the ice cream and the plate. Right. So, say the ice cream initially was at a temperature, say at a temperature of say 5 degrees. Okay. Now, the ice cream is at temperature 5 degrees. So, should it become 10 degrees or should it become say 1 degree? What decides? So, that is the second law of thermodynamics. So, if I have a particular system which is initially say it has a temperature say 5 degrees, and then that goes to say 20 degrees, and the corresponding pressure say was say 1 atmospheres, and then the pressure went up to say 5 atmospheres. So, what we are basically talking about is we are looking at the system, right, at a certain point of time, and we are looking at its pressures, temperatures, volume, velocities, etc. Right. So, it is so therefore, when the system is moving from one state to the other, when its properties are changing. So, we are looking at the change in property, which is entropy in this case. Right. So, in an isentropic process, on the other hand, whenever there is a change in terms of heat supply work done, the entropy change we say is 0. Entropy, the process is such that the entropy change is 0. In that case, how are the pressures, temperatures, densities, etc. related to each other? Right, because there is a change happening, and that relationship is given by something like this. Okay. So, I think that would sort of complete a brief the review of thermodynamics. I think the next thing to do, maybe we should look at some. So, I think with that more or less brief review done, we will try and take a look at some pictures. This is the class is called advanced compressible flow. So, you might be wondering, where are the shocks? Well, so I guess we will just go ahead and look at some pictures of shocks, etc. And before I do that though, we keep talking about, every time we think of compressible flow or gas dynamics, so to speak, we are talking about shock waves, right. And every time we talk about shock waves, we talk about high Mach number flows, right. So, I guess that Mach number is speed by speed of sound, right. Now, so what is this connection with speed of sound? Why Mach number is such a big deal, or why are we going to talk about Mach number when we study something like this, right. And so, we saw the connection between thermodynamics and compressible flows, hopefully. So, now the next question is, what is the connection of a Mach number with compressible flows, right. So, we are talking about changes in pressure, density, volume, temperature, etc., etc. Now, what has Mach numbers to do with it? Okay. So, I think we will start simply, we will try and look at a few things here. Okay. We will look at some interesting things in terms of sound waves, say. Okay. Let us see what sound does. Okay. Before I start, in what way sound is different from say light? What is the difference of sound and light? Well, sound is a material wave, right, unlike light, which is an electromagnetic wave. So, it needs a material medium to travel. Okay. Now, what does that mean in terms of mathematics? We will come to that in next lecture or in a couple of lectures time. Okay. Now, let us do something fun and try to see if there is something interesting over here. Okay. I would like you to pay attention over here and like keep see and listen at the same time. Okay. Be attentive. Okay. Here we go. Okay, we will do that one more time. Okay, we will do that one more time. Okay, we will do that yet one more time. So, what did you notice over here? What did you notice over here? So, you heard the sound first, then you saw the car. And as the car the nature of the sound changed, and as the car passed, the sound also sort of faded off. Okay. Let us just look at that one more time and see what I am trying to say over here. Right. So, you heard the sound first and then the car moved past it. What does that tell you? That the sound reached you faster much before than the car reached you. So, you saw the car much later on, you heard the sound first, right. Okay. So, in that case, let us sort of try and look at a few more things. Okay. So, I have these 4 pictures over here. We will see a few things over here. Now, these black little dots, right, these black dots that you see. So, you can think of these as say the car horn for that matter, or say the source of sound in this case. Okay. Just think of that. Now, in that case, just look at the first one. Okay. All right. Look at this one. I hope you see the difference. We'll kind of redo that a couple of times and we'll try and see what happens. Okay. And we see that one more time. Okay. So, what is the difference between these 4 pictures, or is there a difference at all? Okay. Now, the thing is, in this first first plot, so to speak, the first diagram that we saw, this source or the black circle in the middle, that does not move. In all the other 3 cases, that black circle is moving. So, you can say that the source of sound is moving, right. In the first case, however, it does not move. Okay. Now, these circles that you see is basically each one is a sound wave, right. So, when the car is blowing its horn, so basically it blows its horn, so there is a disturbance, right. Now, that gets transported from here to a certain distance. It is pretty much the simplest to, if I am speaking and you are able to hear right across there, how is the sound moving from where I am standing to where you are sitting, how does that move there? So, it is basically a change in the fluid properties, the fluid in this case being the air, right. So, now that disturbance moves from where I am standing to where you are sitting and you are able to hear it, right. So, similarly here, so what these circles are essentially, these are sound waves. So, these sound waves are moving through the air. Now, what you see in the first figure over here is that the source of the sound itself is stationary. Now, that does not move, okay. But on the second one, what you see is that the source of the sound itself is moving. So, you can see that each of these sound waves, the center of each of these sound waves is also different. Okay. Now, the next thing now the next question to ask is how the important point here is, how is this source of sound moving with respect to the sound waves itself. Now, what you see in this second diagram here is that the sound, the source of sound is moving slower than the sound waves, right. In the second case, the source of sound is moving exactly the same speed at which the sound waves are moving, and in the fourth one, the source of sound is moving quicker. It is moving faster than the sound waves. Okay, so let's sort of look at that. So this is the case where the sound wave, the sound source is stationary, right, and you have the sound waves basically emanating from that stationary sound source. So you have that, and in this case you can see that the sound source is moving slower. It is slower than the sound waves themselves. So then can I say that the sound wave source, basically this is a subsonic case, right. So the speed of that source of sound is less than the speed of sound, right. The next thing is here. So in this case, the source of sound is moving exactly the same speed, right, as that of the sound waves. So I can say this is a sonic case, right. And here you can see that the source of sound is moving faster than the sound waves themselves. So therefore, this is the case where this is a moving faster. So this is a supersonic case. So therefore, what we are able to see here is that you have essentially a sound wave which is moving, right, and how the source of the sound moves and how that compares with the actual disturbance moving, right. Based on that, we said something as subsonic, sonic, and supersonic. Okay, so I think now let us look at some pictures over here. Okay. So this is these are pictures you have probably seen or you are aware of, you have seen somewhere. So this is a bullet that you can see is slightly over the sonic zone, its Mach number is 1.01. And what do you think this is? What are we seeing over here? This is not any actual wire, it is not like an actual barricade. This is actually a picture which is showing a bow shock over here. This is a detached bow shock. Now, what exactly is a shock is something that we will introduce, say, talk about in the next lecture. Okay. So, for the time being, let us just say that this is a demarcation where there is a very sharp change in your properties, with the fluid properties, which is the pressure, volume, density, temperature, etc., etc. So this is that has the interesting part is we are able not just to measure it, but actually see. So I think the innovative part over here is that you are actually able to see a change in pressure, you are actually able to see a change in density or a change in temperature. Just think about it, you can actually see it, and that is a photograph of that. So this photograph is a Schlieren. So usually it's a Schlieren or a shadowgraph. So we will talk about that a little bit, okay, because this is very interesting, and as to how you can use a very basic simple principle in physics to actually capture something like this, something very, very important and complicated actually. So this is a bullet. I would like you to notice the shape of the bullet here, and this is the kind of shock that you get. This is essentially a detached, this disturbance is detached from the body, it is slightly ahead of the body, and this is the bow shock. Okay. Now you can see here clearly, so you can see that you have a sharp nosed bullet which is travelling at a faster Mach, which is 2.35, and you can see that the change in shape of the shock wave, and also it has moved closer, it is attached, so it is attached oblique shock. Okay. So if I may just move back over here, so essentially what I am saying is if I have a blunt nosed bullet like that, right. Now if I sort of make this slightly less blunt or slightly more pointed, then I would expect that this would become a little little more tapered at the edges, and it would probably get a little closer to this bullet, right. So till the time I get a shape something like that, and then it attaches itself to the body itself. right. So, this is an attached Bose shock. So, therefore, the question is that how do I relate that? How do I relate the shape of this body and the shape of the shock and whether it will be attached or not. Now, we will do that. We will do that as we go more into details of this. Let us just look at some pictures and so these are some pictures. What you see over here is condensation in the air. You can sort of do your own research and think these are very interesting phenomena which is happening because of shock waves, and briefly there is a sudden change in temperature, drop in temperature. So, it freezes the it causes freezing in the atmosphere around that. So, that is causing a cloud like that. Okay. You can sort of do your own research. So, then you see several shock waves here, in this picture. Now, this is something you can see traces of shock waves here in the atmosphere right over here, because of this vehicle which broke the sound barrier as well, which is traveling at supersonic speeds. Again you see some shock condensations over here, and this is also something which is an outcome of shocks. So, again you have one more picture here. So, you have this stealth bomber here. So, this is also another picture of showing shock waves. So, okay, so these are some pictures that we saw examples of basically shock waves. What now the next question is this connection of Mach numbers. Okay, so what we will do, I think, in the next few lectures is that we will take a look at, so if I what exactly is a shock wave? Now, that is an important question to answer. So, I think the first thing to do is we will try to answer the question what exactly is a shock wave, right. And the next thing is that how do the properties change across the shock wave, and how are we going to find out? So, if I know the pressures, temperature, volume, etc., say for example in this room, and then suddenly there is a shock wave, I generate a shock wave somewhere here in the middle, by some means, then will the properties change? Well, the answer is yes. Then how will it change? How much will it change? How will I relate those two cases? So, I think that is something we will try to calculate or do it. And the important question is, what is this connection of Mach number now with compressible flows or shock waves? In all the pictures that I showed you, there is Mach 101, it is breaking the sound barrier. The first picture in the first lecture itself, when I said, so we said this was it. So, breaking the sound barrier seems to be a big thing. Now, why? Now, why is the sound barrier such an important fact? Okay. So, what is the connection of Mach number? I think we will sort of do that in the next few classes. So, okay, that should be all. Thanks.